and Moreau will tell us about associated varieties and finite extensions of vertex.
Thank you very much for the invitation. So yeah, you mentioned the title, so yeah, maybe I would like to first recall that there is a contravariant functor from the category of vertex algebras, which associates to any vertex algebra certain affine Poisson that we denote by xb, and this is called the associated variety of the vertex algebra. And so this is defined as an analog of the associated varieties of primitive ideals of the enveloping algebra of semi-simple algebras. Also, the constructions is a bit different. And here also in this setting, this geometrical invariant plays an important role in representation theory of vertex algebra. And more generally, this invariant captures many information about the vertex algebra. So it's natural to try to express in terms of associated varieties some problems about vertex algebras. And here I will be interested in finite extensions in particular. What is interesting is that sometimes you can compute it even if you don't know so well the vertex algebra. So the plan of the talk will be the following. First, I will recall the precise definition of this variety and give some examples. Then I will explain the problem I am interested in about finite extension. And finally, I will consider the case of W algebras, where typically associated varieties are nilpotent Slodovis slices, which have a very nice geometry, and we will use the geometry of Slodovis slice and nilpotent Slodovis slices to study some problem. Okay, this is based on several joint work with Tomoyuki Arakawa and joint works with Jeslo Van Ekeren and Tomoyuki Arakawa. All right, so let me explain how to construct this affine Poisson variety. So let's start with the vertex algebra. So I remind that this is a vector space equipped with a linear map. From V to the space of Laurent formal series with coefficients, which coefficients in the algebra of endomorphism are V. And maybe I denote by AC the corresponding series. And this series is actually a field, which means that this must be 0 for NB now, for any AB. All right, and and this linear map satisfies some axioms. I don't recall all, but in particular, you have the locality axioms, which tell you that up to some power of Z minus W, this bracket is 0. So here this holds in a larger space. And this condition is actually equivalent to the fact that the product between these two fields is can be expressed in terms of some field, and you can understand precisely the singular part of this product. And in the notation of physicists, you write like this. Yeah, and in fact, here, this is the field corresponding to that. So this is equivalent to the complete knowledge of the Lie bracket between AN and BM. All right, and you have also the state field correspondence. Which tells you that you can recover A from the corresponding fields. So more precisely, if you apply your series to the vacuum vector, which is part of the data of your vertex algebra, this is a formal series with only positive term. And so it makes sense to evaluate at z is equal to 0. And in this way, the axioms tells you that you must recover A. All right. Okay, so now from this purely algebraic structure, you can associate a certain Poisson algebra in a canonical way, as follows. Maybe I should start with, okay. Okay, so let's consider the following subspace of V generated by vectors of this form. So in terms of fields, you can also understand this slightly differently. So assume that V is finitely generated by some field. So it means that you can write, there are finitely many fields, let's say A1, R, like this. And then your vertex algebra is expressed just in terms of the derivative of these fields. And then you take the normally order product just to make this product, it makes sense, okay? So using this description here, C to V is just the span of such vectors where the same, where N1 plus NR is greater than 1. So you kill all derivative each time you have one derivative. All right, and then we can consider the quotient. And this is naturally Poisson with the following Poisson structure. So first of all, the product is just given by the normally ordered product. So just the image of A minus 1B. So I denote with a bar the image in the quotient. So in terms of field, you can write, this is just the image of the normally ordered product. And the Poisson bracket is given by the 0 endomorphism. So here, so in terms of fields, you get something like that. Right, so, and of course, the unit is given by the image of the vacuum. Okay, so this is a Poisson algebra, and the associated variety, just a reduced scheme associated with this Poisson algebra. Start with this. And so XV. So maybe it's also interesting to consider the scheme associated with RV, and then the reduced scheme I will denote without tilde. So this is how we construct this invariant. And as you can expect, the nicest vertex algebras are those for which this is as small as possible. So in particular, if it is just a point, then V is has very nice properties. So let's say that V is least on C2 cofinite if XV is just a point. Yeah, I will also assume that V is conformal. So in particular, V will be always Z-graded by the action of the Virasoro element. Okay. So yes, it's true that this is equivalent to that condition, and this is equivalent to the fact that RV is finite dimensional. So these vertex algebra are very nice. So for instance, if V is Lis, and maybe I assume also rational for the statement, then first of all, there are only finitely many V modules, simple V modules. So this is already very strong properties. And moreover, if you consider the corresponding normalized characters, they have very nice modular invariance property. So moreover, for such an element, if you consider the normalized character, so which is so this is C is the central charge, and L0 is a semi-simple element coming from the Moreau algebra. So this and Q is like this. So this function converges to a holomorphic function on the upper half plane. And moreover, if you consider the vector space generated by all these characters, then this is a finite dimension. So this is an example of properties you get just as looking at the associated variety. So let me give some examples and non-examples.
Does this grading go survive to the Poisson algebra as well?
Sorry?
Is the Poisson algebra graded? Is that graded?
So it's graded from you can also construct the Zoos algebra. So in fact, yes, it's graded from that, but to see that, you can consider the Zoos algebra, which is a filtered algebra. So typically you get the enveloping algebra for the example I will get. And then Greux of that can give you a grading on RV. So it's similar to that, yeah. But it comes from the conformal grading. Yeah, in fact, thanks to my assumption, conformal, this is conical. But in general, it no needs to be conical. Okay, so let's give examples. So let's consider the 6 complex number, and let's consider the following representation of I have to say, so G here is simple, and I consider certain invariant non-degenerate bilinear forms. So in practice, I like to consider the following normalization of the killing form. And then I consider the affine Kac-Moody Lie algebra associated with G and this bilinear form with usual Lie brackets. And then I consider the following induced representation of G hat. Okay, well, here this is a one-dimensional representation of this parabolic subalgebra. Where CT acts trivially and K acts as K identity. All right, so this is a representation of G hat, and it is well known that it is also it has also a natural structure of vertex algebras. So this is a universal affine vertex algebras, and here the OPE. So OPE is what I denoted with AZBW. First of all, this vertex algebras is generated by element in G, which identify to the degree 1 component. And and write corresponding fields here. So this acts as by left multiplication on your space, and the OPE are given by, in fact, are equivalent to the Lie bracket in G hat. Okay, so here it's not difficult to see that the associated variety is just the dual space of G. And more precisely, the quotient RV is just the symmetric algebra of G. Yeah, that's a, I don't know who asked the question, but yeah, that's a very good remark. So for the universal one, it does not depend on K, but I will consider a quotient, and the quotient depends, the variety will depend on K. Yeah, so here, so this is just G star with the usual constant Korylov-Sourillot-Poisson bracket. And here it's even true as a scheme. So indeed, it does not depend on K. But now in general, this vertex algebra is not simple. And then I consider the unique simple quotient. So either as vertex algebra or as a G hat representation, because in fact it's equivalent. This is in fact a irreducible highest rate representation of G hat. And here, this is really an analog of associated varieties of primitive ideals, and because this is an irreducible highest rate representation. But contrary to what's happened for primitive ideals, this is not always contained in the nilpotent cone of G. So in fact, in general, it's not contained in the nilpotent cone. So in fact, it may happen that this one is already simple. So obviously, in this case, it is not contained in the nilpotent cone. And more precisely, with Tomoyuki and Shuipo Yang, we recently proved that this one is simple if and only if the associated variety of the simple quotient is precisely that I can identify with G. All right, okay. But there are many families for which it behaves similarly to associated varieties of primitive ideals. And in particular, there are some examples where this is a Lie actually. So what we can say is that if I can say that this one is Lie, so that is to say this is just a point, just zero. If and only if, as a G hat representation, this is integrable. And it is well known that this is equivalent to the fact that K is a non-negative integer. So here it's a Lie example, but here the corresponding quotient is not reduced at all. So still the structure can be interesting, also it's just a point. And as you can see, this is quite restrictive. You obtain only integrable representation for least simple affine vertex algebras. So let's give another example. Of different nature.
Sorry, and does the critical level somehow distinguish in this?
Yeah, here no, because this is not critical, but okay, I will assume later it's not critical, but for critical level, you have exactly the nilpotent code. Yeah. So.
Is it known what the non-reduced scheme is?
Yeah, yes, at least for SL2, yeah, you can compute it. Yeah, it's easy to describe because it just power on here. I think it just dimension 5 for SL2, for instance. It's just something like yeah, so yeah, maybe I should mention that this one is just the coordinate ring over this. And essentially, for integrable case, it's generated by singular vector, and you have, yeah, it's generated by the highest root vector as a G module. So for SL2 is easy to describe. Yeah, for SL2. For, sorry, SL2 and K is equal to 1, for instance. Of course, it's bigger, so it's maybe so. It's an exercise. Yeah, yeah, it's easy.
On and the answer at the bottom there is symmetric algebra residual mod the ideal generated by E theta.
Yeah, sorry. Here it depends on K.
E theta, that's what it says.
Yeah. Yeah. Here, sorry, here it depends on K. So, yeah, this is, yeah, you take the highest weight vector of the adjoint representation and then you take a power K plus 1. In general, it's not known. Now, for arbitrary K, this is not known. But for integrable case, we know it's the simple quotient is generated by singular vectors, and we know explicitly how to compute it. Yeah, so let's consider a different style of example. Let's consider C2 with a coordinate PQ and natural simplex structure. So this admits a natural quantization with the Weil algebra, but it also admits nice chiralization. That is to say, vertex algebras whose associated scheme is exactly this. If you consider the beta gamma system, usually denoted like this, generated by two fields. And with OPE. Given by this formula, and this is a natural chiralization in the sense that the associated scheme is just the symplectic varieties obtained from the beginning with the corresponding Poisson structure. So here it's not Lis, but still it's nice because it's symplectic. And in fact, also smooth, obviously, reduced. And with Arakawa, we prove that in such situation, this implies that the corresponding vertex algebra is simple. So in this easy example, it's easy to check directly, but this is true also if you replace C by any symplectic scheme. Okay, so this is another example of what you can detect from the associated scheme. And more generally, if your associated variety has only finitely many symplectic leaves, then the corresponding vertex algebras is supposed to be nice. Yeah, so more generally, if XV has finitely many symplectic leaves, then okay, I just say it's nice. So you have similar properties to the what I mentioned for the leaks case. You just have to restrict to some particular simple V modules, and the modularity properties is a bit weaker, but it's similar. And then this is due to Arakawa and Kawaki. All right, so let's give more examples. So I return to this setting. So in fact, if you consider a larger class, if you consider admissible representations, So these representations are supposed to, conjecturally, they correspond exactly to those representations whose characters has modular invariance properties. This is due to Katz and Wakimoto. The definition, I don't give the general definition, but here it just means that K is a particular rational number. So this is a dual Coxeter number. And then you have P and Q, two integers, which are co-prime, and P is greater than the dual Coxeter number if Q is co-prime with velocity, so type AD. It's one for type AD, but it's defined all the time. And P is greater than the Coxeter number if Q is not co-prime with velocity. Okay, so if in such situation it was proved by Arakawa that the associated variety is the closure of some nilpotent orbits. So in particular, it's contained in the nilpotent cone, and in particular, it has only finitely many symplectic leaves. And in fact, there is a precise description. At least in the first case, it's quite precise. And you have similar in the other case, but I don't give specific descriptions. And yeah, we have a few more cases outside admissible level, but maybe I want now to explain examples for W algebras.
The last equation, is that a joint?
No, it's 0, 0.
There's an X, I think, missing on the left side.
Yeah. Sure. Yeah, so in SLN, it corresponds to almost rectangular partitions. Okay, so now let's last family of example I want to discuss is now fix a nilpotent element. You can embed it into an SL2 triple. And then consider the corresponding Slodovy slice. So this is a transversal variety to adjoint orbits or co-adjoint orbits, but I identified it also. All right, and it is a Poisson, and the Poisson structure comes from the Poisson structure on G star by Hamiltonian reduction. So this variety admits also a natural quantization, which is a finite W algebras. That were studied by Premet, Lozef, and other people. So it quantization in the sense that the Zoos algebra, just graded algebra of that is just a coordinate ring of that one. And also it admits Carolization. Which are the W algebras associated with G and F at level K. Here you have one family of vertex algebras whose associated scheme is exactly as F. So this is defined by the Drinfeld-Sokolov reduction. So that is to say the BRST cohomology associated with the Drinfeld-Sokolov reduction associated with F applied to the universal affine vertex algebras. So here it is known that the associated scheme, of this one is the Slodovi slice due to cats and the solid. So here again, you notice that it does not depend on K. But when we take here also the quotients, simple quotients, it will depend on K. So in general, for a nilpotent orbit O, you can consider the corresponding nilpotent Slodovi slice, which is the intersection of the closure with this Slodovi slice. So this is interesting because it captures the local geometry of your nilpotent orbit closures. And for some nilpotent orbits, this also appears as associated variety of the simple quotient of the W algebras. Not all orbits appears in this way, but the reason is that by a result of Arakawa, the functor, the Drinfeld-Sokolov reduction is compatible with the functor of associated scheme. More precisely, the associated scheme of the Drinfeld-Sokolov reduction applied this time to the simple quotient, and more generally any quotient, is the scheme theoretic intersection of this associated scheme with the nilpotent slice. So in particular, the reduced scheme is just an intersection. So as soon as you know how to compute this, you know how to compute this. So unfortunately, it's not clear whether this is exactly the simple quotient, but conjecturally it is. So if you talk, maybe I will don't care about that, but simple quotient. So conjecturally, this one is non-zero. And it's easy to check whether it's non-zero thanks to this result. All right, so in particular, you see that if K is admissible, this kind of varieties appears as associated varieties of W algebras. So you see that these nilpotent Slodovic slices appears in many areas of mathematics. And this is interesting for us. I should start with something. Yeah, so these objects, of course, it is known that they appear in the theory of symplectic singularities. In fact, they were studied, motivated by the normality of nilpotent orbit closures. They were studied by Kraft-Rochesi in the 80s for classical types. So essentially, the singularities of this are understood in this setting. And much more recently, they were considered, at least for a generic case, by Fu, Juto, Lewy, and Sommers for exceptional types. So actually, the knowledge, the complete knowledge of these varieties is not completely understood in general, but they consider many cases. And more recently, so this is 2017, Bellamy and Bonafé joined that group to study more examples, if I am correct. So this is very interesting for us because, as I mentioned, this also appears as associated varieties of W algebras, some W algebras. And of course, we use the geometry, the singularities of these objects to study some of our problems on W algebras. And conversely, sometimes we have new light on this more classical theory using our results. And also it appears in physics as X branch, some 4D n is equal to 2 superconformal field theories. And here the two facts are connected by the H branch conjecture. By Bean and Rastelli. Which claims that the X branch of such theory, so it's X branch, can be recovered by considering the associated variety of the corresponding 4D chiral algebra. So in other words, the corresponding vertex algebras. So I don't explain so much here this 4D to D duality, but the idea is that you can associate to such theory two-dimensional conformal field theory, so a vertex algebra, and then you can recover this invariant taking the reduced associated variety. And W algebras at some admissible levels appears in this context. So what is very interesting is now Rastelli conjectures that actually, if you take the associated scheme, this should be a complete invariant. This one is not a complete invariant because many theories has a trivial X branch and very different vertex algebras as trivial associated variety. But if you consider the associated scheme, it contains much more information. Okay. Okay, so I think I finished for the examples, and now I would like to explain what I want to say about finite extensions. Any questions?
And something I might have missed is, can you always recover the vertex algebra from the associated scheme?
This is what Rastelli hoped or hopes.
But that's for like maybe particular families. Is there anything known mathematically?
So what he claims is that this should allow us to recover. So I mean, it's a complete invariant in the sense that if two theories have the same, they should be the same. This is what he explained to us. For instance, you can, what we are trying to do with Arakawa is to recover, for instance, the R filtrations. So in physics, I don't know exactly what it means, but in mathematics, we have a candidate. So it's kind of invariant that you cannot detect from this, for instance. Yeah, so what we want to consider is that, let's consider a conformal embedding of vertex algebras. So it means it sends a conformal vector here to the conformal vector here. And then it induces a morphism of Poisson variety like this. And then you can consider the comorphism and take the reduced scheme corresponding to that. So let's say this is phi, so you take corresponding reduced homomorphism, and I like to call it pi. And then you have a map like this. And we want to say that when the extension is finite, so a conjecture that if, so more precisely, the extension is finite, I mean that W is a finite sum of V mod, simple V modules. And I assume it is ordinary. So I assume that each MI is graded and bounded from below. So, technical condition, but like this, and all PCs are finite dimensional. Okay, so under this condition, and the conjecture is that pi is dominant. Okay, so it is known in particular that it is known that if V is finite, is least, so if this is a point, this one is a point. This is known. So our conjecture suggests that the contrary is also true. The converse is also true.
Why is this map? Why is the map on associated varieties? Is that right?
Yeah. Just consider the corresponding map of associated variety. And it's not true for infinite extension because, for instance, if you know the lattice vertex algebra, maybe I'll do two remarks. So the conjecture suggests that if V is least, this is equivalent in the setting of the conjecture. This one is also least, so one direction is known, but the converse is not known. And second remark is that is not true for infinite extension. Actually, we don't know whether it's true also here because we don't have results for the moment, but at least it's not true for that. For instance, if you take the lattice vertex algebra, it contains the Heisenberg vertex algebras. This one is known to be least and this one is not. The associated variety is just H stars. Okay. So yeah, we don't have a result for the moment. In the setting where V, in this case where V is a simple affine vertex algebra, we can say a bit more. And we check somehow case by case in the setting of W algebras for admissible levels, but it's not really satisfying for the moment. But I want to explain what it means geometrically. So so one thing we can observe is that if V is simple, let's say exactly this, simple affine vertex algebras. Sorry. Yeah, it's fine. But in fact, this it is what I want to assume for my proposition here. Because we don't know whether the conjecture is true, you can put whatever you want. But maybe we conjecture we don't, just finite extension is fine. But here, I need to assume that W is really as before. All right, and then what we can say is that at least the extension from the image to our W is finite. So this is not enough, but at least it implies if, in particular, if XW and XV are irreducible, that we conjecture to be true for the case they have only finitely many symplectic leaves, then the dimension of this one is always bigger, smaller at most the dimension of XV. So to prove the conjecture in this setting, it's enough to check that the dimension is bigger. So it's not trivial, but at least we reduce to something which looks a bit more reachable. Yeah, so to finish, I would like to explain the meaning of that in the setting of W algebras. Any questions? So I don't explain the proof, but in fact, it's not so hard to find strong generators from this decomposition. And from the strong generators, you can compute explicitly RW, and it's nothing complicated. Yeah, so let's go back to the setting of W algebra. So remember the SL2 triple. So you can consider the centralizer in G of this SL2 triple. So let's consider the centralizer of this SL2 triple. So it is known that this is a reductive Lie algebra. It's an algebra of G. And in some sense, this acts on your W algebras. So more precisely, you have a vertex algebra homomorphism from the universal affine vertex algebra associated with G natural for some level. You have an embedding here. And then you can consider the projection onto the simple quotient. And you can wonder whether this factorize or not. So in general, not. But what we show is that if the morphism, if this one is conformal, then it factorizes, and we have a purely combinatorial conditions to prove that in the case where K and K natural are admissible. So because I don't have so much time, I explain this directly. So yeah, I state like that. So if this one, so the composition map is conformal, then we have an embedding like this. But here I assume K and K natural admissible. So in fact, K natural is entirely determined by K, so you just need to assume K admissible. Yeah, in fact, this is a finite extension in this case. It's automatically a finite extension. And in fact, what I want to say more is that we have also a criterion to say when this is exactly isomorphic to that. Okay, maybe I say the same theorem. And if, yeah, so this is the first part. And second, how to detect whether it's conformal. What is nice is that, in fact, if V, okay, let's say is either this or it's Drinfeld-Sokolov reduction. In fact, we have a more general result for any vertex algebra whose associated variety has only finitely many symplectic roots. But let's assume this setting. And then the normalized character has a asymptotic behavior. So it means that it has, sorry, it's G. It can be written as follows. Yeah, I'm not sure of the constant. It's not important. G is here. Yeah. When tau goes to 0 through the imaginary line. Okay. And then here AV and GV are some constant. So the meaning of that is that the asymptotic, the normalized character has a nice asymptotic behavior. And moreover, we can compute this explicitly. And moreover, in our setting, if GK natural coincide with the Drinfeld Sokolov reduction of this one, then F is conformal. So this gives a kind of combinatorial criterion to have a finite extension. And it's really combinatorial because this can be computed explicitly in terms of the, so depending of this or that, it's completely explicit. And moreover, if now what we call the amplitude is the same, it's really an isomorphism. And what is nice is that it's enough to look at the Drinfeld Sokolov reduction and you get really about the simple quotient here. Then we have an isomorphism, and in this case, this is what we call collapsing. Okay, so sorry, I'm a bit quick, but the idea is that in the admissible level setting, we are able to, we have a criterion to detect either whether this is an isomorphism or a finite extension. And this is a way we have a big list of examples, and we conjecture that all examples we find actually are the exhaustive list of collapsing admissible levels. And also for finite extension, we have to be a bit more careful, but also we expect to find all. And also using the amplitude here, even in the setting of finite extension, we can explicitly describe the finite extension. Okay, so to finish, I would like to explain the geometrical meanings to go back to the conjecture in this setting. So what is a morphism pi that appears in our conjecture?
When does collapsing, like in practice, when does it happen? Like you have a criterion, but
This is a good question. So in fact, it was introduced by Adamovich, Cox, and so on for minimal case. And this in practice, you can compute because you know OPEs in this case. But for general F, we don't know OPEs. So precisely, we have used geometry to find candidates. Because if it is collapsing, the associated variety must be isomorphic. And this is what I want to explain. This means that some nilpotent Lodovi slice must be isomorphic to the nilpotent orbit closure in something smaller. And then this we know thanks to the works of people I mentioned. We know we have example where it can happen. Then we have candidates, and our criterion is useful to prove it's indeed the case.
how level dependent is that?
Highly depends on the level. Yeah, because the geometry just tell you what could be F, first of all, and then you have candidates because you look at, for instance, central charge of this.
And
And-
then you compute the characters to figure
Yeah,
out which
we don't compute the characters. This is the point. We just need to compute this and this. Yeah, I will explain on examples. Yeah. So, yeah, what is the morphism? So maybe let's start with this. I mentioned we have something like this. So the corresponding morphism of associated varieties, it just, so remember the associated scheme here is Lodovi slice, and here you get just G natural. So in fact, the dual, but identified with this. And what is this? So this, I remind you that this is F plus the centralizer of E, and this is positively grading for the Dinking grading. So you can write an element here, F plus X0, but G E0, as you know, is just G natural, plus positive part, and it's just a projection. So this is easy to understand what is a homomorphism. And now, when it's a finite extension, the simple one, is a finite extension, then pi is just a restriction to the corresponding nilpotent orbit closure. So it's the same morphism, actually. So in general, it's not true that if you take any nilpotent Slodovi slice, you can do the same. It's not true in general that this is dominant unto a nilpotent orbit closure of the same dimension. But here, we can check, but case by case for the moment, that the dimension of this is always the dimension of the image. So here, more precisely, it goes to this dimension as the same. We hope to be able to use this equality to prove something about the dimension, but for the moment, this is not clear. So let me give examples. So I give two examples. First, in the setting of collapsing levels, so when it's really an isomorphism, and the case where the two varieties are not isomorphic, but we have a dominant morphism. So let's first consider the case G is SLN. Okay, and we have a generic family of, we have a large family of example. Here, let's write the Euclidean division. So I fix Q, N like this. Okay. No, sorry, I fix an admissible level. Yeah. I fix Q. With PQ co-prime and P is greater than N. Okay, I take the Euclidean division of N by Q. All right, and by Arakawa's result, the associated variety here is given by this partition. All right, and now I pick in this nilpotent orbit element F associated with partition of this form. Don't really care what is M, what is S, you just want it is in the closure. Okay. So you have a partition like that. So this is this one, and you want to, and then you take F here. You have F in a partition of this form. Okay. And our statement is that as in this setting, this one is collapsing, and more precisely, this is isomorphic to this one. And here, G natural is just C cross SLS. Okay, so this is an example of collapsing level. And this was predicted by some physicists because it appears in the 4D to D duality. What is the geometrical meanings of that? What is the associated variety of that is the intersection. And maybe some of you knows, but the Kraft-Prochézy rules tell you that if you erase the common rules, the nilpotent Slodovi slice is isomorphic to what is left. So you have Q something, intersect, it is intentionally we get the zero orbit. And what is left is exactly the closure you get here. So this is how we find F a good candidate for collapsing level. So this is to answer your question, this is how we find many examples, and it works similarly for other classical types. And for exceptional types, you have finitely many cases, so we can also check all. But we started with Juto et collaborators examples to find the examples. And then I want to give maybe one example for finite extension. So maybe I choose well F4. Now maybe G2 is faster. Now let's take G2. So now I would like to give an example in G2 of finite extension. So for instance, we obtain, as I mentioned, so here F is a minimal nilpotent orbit of G2. And then we prove that this is a finite extension, sorry, of SL2. Here you have some weights, inadmissible weights, so just a fundamental weight. And then pi, what is pi? So what is the corresponding Slodovich slice here? Here you get the second smaller nilpotent orbit in G2 with A1 and to the nilpotent cone of SL2. So this has dimension 2, of course. And this dimension is 8, and here it's 6, so you have also 2. So it's indeed dominant. And it's not isomorphic. Actually, this one is known to be not normal. So this is an example where the associated variety have the same dimension, they are irreducible, but they are not isomorphic. And we have similar example in F4. What is interesting is that you can compute explicitly the generic fiber, and here you find 2, and when we have 3, sometimes we find 3, etc. So we expect a connection between the cardinality of the generic fiber and the number of modules. Sorry, I should stop.